Some research facilities are pushing the boundaries of science in environments where danger is part of the job. From labs handling deadly viruses to sites studying nuclear technology, these places operate under the highest security. Join me for today's video. We're counting down the 15 most high-risk research facilities in the world. Starting with number 15, Biosafety Level 4 Labs. Biosafety Level 4 laboratories are among the most high-risk research facilities in the world, designed to study the most dangerous pathogens known to man. These pathogens, including viruses such as Ebola, Marburg, and Nipah, pose a significant threat due to their high transmissibility and the lack of effective vaccines or treatments. Understanding these facilities, their history, operations, risks, and benefits provides some insight into their critical role in global health and safety. BSL-4 laboratories represent the highest level of biocontainment precautions required for handling agents that can cause severe disease through aerosol transmission. These facilities are designed to prevent any release of biological agents into the environment. Now, they're located around the world, with notable examples in Winnipeg, Canada at the National Microbiology Lab and Atlanta, Georgia at the Centers for Disease Control and Prevention. There are currently 42 operational BSL-4 labs globally, with more under construction. Work in these labs requires some precautions. Researchers wear positive pressure suits, ensuring that even if the suit is punctured, air flows outward rather than inward. Entry and exits involve airlocks, chemical showers, and extensive decontamination procedures. Lab airflow is tightly controlled to ensure that air only flows inward, preventing the escape of potentially contaminated particles. The danger of working with pathogens in a BSL-4 lab lies in the possibility of a containment breach. If a pathogen were to escape, it could potentially cause an outbreak with serious health consequences. Historical records show that laboratory-acquired infections have happened at lower biosafety levels, but no known catastrophic containment failures have been attributed to BSL-4 facilities. However, accidents have highlighted the importance of stringent protocols. But despite the risks, BSL-4 laboratories are indispensable. They allow scientists to study pathogens that pose the greatest threats, often referred to as Disease X, emerging infections that could cause the next pandemic. These labs are also essential for zoonotic disease research, where pathogens jump from animals to humans, and as urbanization and habitat destruction increase the frequency of these spillovers, BSL-4 facilities provide insights into preventing these threats. Number 14, the National Ignition Facility. The National Ignition Facility, located at Lawrence Livermore National Lab in Livermore, California, is one of the most advanced research facilities in the world. Completed in 2009 after over a decade of construction, NIF houses the world's most powerful laser and serves as a critical hub for nuclear fusion research. The primary function is to explore the feasibility of inertial confinement fusion. This involves focusing 192 high-powered lasers onto a tiny fuel pellet containing deuterium and tritium, isotopes of hydrogen. These lasers deliver energy so intense that they cause the outer shell of the pellet to explode outward, forcing the fuel inside to compress and to heat to temperatures exceeding hundreds of millions of degrees. This implosion mimics the condition found in stars and thermonuclear explosions, creating a brief but powerful environment for fusion reactions. The pursuit of nuclear fusion holds the potential to revolutionize energy production. Fusion reactions produce no long-term radioactive waste, emit no greenhouse gases, and rely on fuel sources that are abundant and widely available. If successfully scaled, fusion could provide a sustainable solution to global energy demands. But to mitigate any risks, NIF employs rigorous safety protocols, including advanced monitoring systems, redundant containment measures, and strict procedural guidelines. Each experiment undergoes extensive computational modeling and review before execution, ensuring a best possible level of control. The materials used in these experiments, like beryllium and small amounts of plutonium, introduce some additional hazards. Handling and disposing of these materials require facilities and protocols to prevent any contamination or accidental exposure. Although no major incidents have been publicly reported at NIF, the theoretical dangers associated with high-energy laser operations and nuclear material experimentation make it one of the most carefully managed facilities of its kind. Number 13. Chelyabinsk 70. Chelyabinsk 70 is one of the most secretive and high-risk research facilities in the world. Founded in 1957, this closed city is located near Lake Samara in Russia. It was established as part of the Soviet Union's nuclear weapons program and remains one of the two primary centers for Russia's nuclear research. The city was granted official town status in 1993, but its access remains tightly restricted, even to Russian citizens. Chelyabinsk was conceived during the Cold War at a time when the Soviet Union was racing to establish a nuclear parity with the United States. Within months of its founding, the scientists at the facility designed and tested a thermonuclear device, marking a major milestone in the Soviet nuclear program. Today, it's home to approximately 49,000 people, many of whom are scientists, engineers, and support staff. The security surrounding it makes it difficult to confirm any specific incidents, but the risks associated with nuclear research are well documented. Accidental release of radioactive materials have happened in other parts of Russia, such as the infamous 1957 Kishtim disaster at the nearby Mayak facility. While no comparable event has since been publicly reported at Chelyabinsk, the possibility of accidents remains an ever-present threat. Another concern is the facility's aging infrastructure, which, like many Cold War-era installations, may not meet modern safety standards. But despite the challenges, they're essential for maintaining and modernizing a nation's nuclear arsenal, which some governments consider vital for deterrence and national security. Additionally, research conducted at these facilities can lead to advancements in related fields, including materials science, energy production, and computational modeling. Number 12. The Barrow Arctic Research Center. The Barrow Arctic Research Center, located at Utqiagvik in Alaska, is at the northernmost tip of the United States, and it's one of the most remote and high-risk research facilities in the world. This research hub is at the forefront of studying the impacts of climate change in the Arctic, one of the most rapidly changing environments on Earth. The Arctic presents unique challenges that make every research mission here potentially dangerous. Utqiagvik experiences extreme cold, with temperatures regularly dropping well below freezing. The region is also semi-arid, with just 150 millimeters of annual precipitation. But one of the most significant hazards is the permafrost itself. As the ground thaws due to rising temperatures, it becomes unstable, potentially compromising structures and transportation routes. Melting permafrost can also release previously trapped greenhouse gases, accelerating global warming and increasing the urgency of the research. Operating in such an extreme environment requires strict safety. The Arctic climate, with its temperatures, storms, and infrastructure, demand careful planning for every field expedition. Researchers have to carry specialized gear, including cold weather clothing and survival equipment. Transportation to the field sites often involves snowmobiles or aircraft, adding some logistical complexity. Despite the dangers, though, the Barrow Research Center is indispensable for understanding that the planet's climate is changing, and the Arctic serves as a bellwether for global environmental change, warming at a rate nearly 4 times faster than the rest of the world. The research conducted here has also practical applications beyond the Arctic. Studies of atmospheric composition, for example, contribute to global air quality monitoring and the development of climate models. Insights into permafrost dynamics can also help communities worldwide prepare for the impacts of thawing ground. Number 11. The Japanese Sakurajima Volcanology Observatory. The Sakurajima Volcanology Observatory is situated near the base of the Sakurajima volcano in the Kagoshima Prefecture in Japan. It's one of the most high-risk research centers in the world due to its proximity to one of the planet's most active volcanoes. The observatory operates as part of Kyoto University's Disaster Prevention Research Institute. Its primary mission is to monitor volcanic activity and provide data to better predict eruptions. Using a network of seismic instruments, gas detectors, and cameras, researchers track lava flows, pyroclastic activity, and ash emissions. These efforts allow for the issuance of timely warnings to protect both the local people and the broader region. Volcanic ash can damage sensitive equipment, clog air filters, and cause respiratory issues, and researchers have to wear protective gear and use specialized tools designed to withstand those conditions. Despite the precautions, though, the threat of sudden explosions, pyroclastic flows, and rock falls that remain ever present. The facility works closely with local authorities to develop evacuation plans and ensure the safety of the population in the event of any significant eruptions. The insights gained from this observatory have improved eruption forecasting methods, not just for Sakurajima, but for other active volcanoes around the world. By analyzing seismic patterns and gas emissions and other precursors to eruptions, researchers can better understand the complex process that drives volcanic activity. That research has practical applications far beyond Japan, helping to safeguard communities near any active volcanoes globally. Number 10. The International Thermonuclear Experimental Reactor, France. The International Thermonuclear Experimental Reactor stands as one of the most ambitious and high-risk projects in the world. It's located in southern France. ITER, as it's also known, aims to create energy through nuclear fusion, the same process that powers the sun. The project is a collaboration between 35 nations, including the European Union, United States, Russia, China, and India. When completed, ITER will be the largest fusion reactor ever built, with a plasma volume 6 times larger than the largest operating fusion reactor today. The project holds the potential to revolutionize energy production, but its very nature makes it a facility of immense danger, requiring precautions and oversight. ITER's primary objective is not to generate electricity, but to demonstrate the viability of nuclear fusion as a large-scale energy source. The project's ultimate goal is to prove that it is possible to achieve a burning plasma where the fusion process produces more energy than it consumes. This experiment is essential to develop a commercial fusion power plant in the future, and ITER will provide valuable insights into technologies like cryogenics, heating systems, and plasma diagnostics. Fusion reactors, unlike traditional fission reactors, don't rely on chain reactions of splitting heavy atomic nuclei. Instead, they fuse light atoms, typically deuterium and tritium, to form helium and release energy in the process. At ITER, the fusion reaction takes place in a toroidal-shaped magnetic confinement device known as a tokamak, which uses a powerful magnet to control and stabilize the plasma, which is a hot, electrically charged gas that can reach temperatures of over 270 million degrees Fahrenheit. The challenge is to keep this plasma contained in the reactor without it touching the reactor walls, which could cool it down and stop the process. A runaway fusion event, while extremely unlikely, could lead to the release of high-energy particles that could damage the reactor and its components. However, the safety systems in place at ITER are designed to contain these incidents with minimal consequences. A fusion reactor, even in the event of a malfunction or breach, is highly unlikely to experience a runaway chain reaction or release any significant amounts of harmful radiation. A fuel for a fusion reaction is also far less potent than the uranium or plutonium used in fission, meaning that any accidental release of material would have much less of an environmental impact. Number 9. The Mount Erebus Volcano Observatory. The Mount Erebus Volcano Observatory is located on Ross Island in Antarctica, at the base of Mount Erebus, the most active volcano in Antarctica and the southernmost active volcano on Earth. MEVO is not only one of the most high-risk research labs in the world, but it also provides valuable insights into volcanology, geophysics, and even the potential for life in extreme conditions. Unlike many volcanoes that erupt only sporadically, Erebus is continually active, with a 1700-degree Fahrenheit lava lake bubbling at its summit. This lava lake is one of only 5 known lava lakes in the world, making it an extraordinary feature for research. These lakes are a key focus at MEVO, providing insights into the volcanic process, the nature of magma, and the dynamics of eruptions. But working at MEVO is not for the faint of heart. The combination of extreme cold, unpredictable volcanic activity, and the remote nature of the location makes this incredibly hazardous. The frigid temperatures down there, often well below freezing, create immediate risks of frostbite and hypothermia. At the same time, the volcano presents its constant dangers. The eruption of volcanic bombs, gas emissions, and the instability of the lava lake all pose significant risks. One of the more significant hazards comes from the ice caves, which are formed by volcanic gases. These structures can collapse unexpectedly, trapping those who might be exploring or studying them. The constant release of volcanic gases is also dangerous, as some of these gases are toxic, including carbon dioxide, which can accumulate in low-lying areas and suffocate anyone nearby. Despite the dangers, the need for research at MEVO is compelling. The constant volcanic activity here provides a rare opportunity to study volcanoes in a consistent and ongoing manner. By studying it, researchers can gain insights into the eruption patterns, magma behavior, and the role of gases in both the formation of ice caves and the eruption process itself. Furthermore, the extreme conditions here in Antarctica allow scientists to explore the possibility of life in environments that mimic those of other planets, making the research at MIVO not only valuable for Earth-based science, but also for planetary exploration, which is cool. Number 8. Diamond Light Source. The Diamond Light Source is a state-of-the-art synchrotron facility located at the Harwell Science and Innovation Campus in Oxfordshire, England. This scientific powerhouse is known for the ability to generate intense beams of light, from X-rays to the far infrared. These beams are essential for research at the atomic and molecular levels, enabling groundbreaking studies in materials science. At the core of Diamond is its synchrotron, which accelerates electrons to nearly the speed of light and then directs them around a large circular path. This process creates highly concentrated beams of light which are channeled through beam lines for use in scientific experiments. With an energy of 3 giga-electron-volts, Diamond produces light up to 1 billion times brighter than the sun, and even a small exposure to this beam can be dangerous. It's got 32 beam lines dedicated to various scientific fields, including biology, archaeology, and material engineering. These experiments range from studying proteins to uncovering details about historical artifacts like the Mary Rose, King Henry VIII's flagship. But Diamond's operation is not without its hazards. The most obvious danger comes from the synchrotron radiation itself. These are X-rays produced at these extreme intensities. These beams are capable of damaging any biological tissues, and as such, strict safety protocols are in place to protect researchers and staff. Even brief accidental exposure could have serious consequences. To mitigate risks associated with working at Diamond, the facility employs a range of measures. First and foremost, strict protocols govern access to areas where radiation is present, ensuring only authorized personnel are permitted. Workers are equipped with protective gear, and experiments are often conducted remotely to reduce any exposure. This facility is also equipped with backup systems and redundancies to protect against any power outages or environmental disruptions. Because the location is prone to severe weather, the building is also designed to withstand any extreme conditions, and a special insulation to prevent freezing and structural reinforcements to handle storms. Moving on to number 7, JPL's Spacecraft Assembly Facility. Located at NASA's Jet Propulsion Laboratory in Pasadena, California, the Spacecraft Assembly Facility is one of the most critical research labs in the world. Here, NASA engineers work on cutting-edge technology to build missions for the Moon, Mars, Venus, Jupiter, Saturn, and beyond, including the iconic Mars rovers, the Voyager spacecraft, and Earth-observing satellites. Its most notable features are its 2 clean rooms, High Bay 1 and High Bay 2, which provide a controlled environment free of dust, particles, and microbes that could interfere with sensitive instruments. These clean rooms are designed to protect the equipment from contamination, ensuring that nothing from Earth makes its way onto distant planets, moons, or asteroids. Each clean room is classified as a Class 10,000 environment, meaning they maintain fewer than 10,000 particles of 0.5 microns or larger per cubic foot of air. This level of cleanliness is necessary to ensure the success of the missions, especially those that search for signs of life on other planets. In fact, the SAF is built to be the cleanest room on Earth, making it an extremely high-risk area in the field of research. Any failure to keep the facility clean could result in catastrophic consequences, including false discoveries of life on distant worlds. For instance, if bacteria or microbes from Earth hitch a ride on a spacecraft, they could be mistakenly identified as alien life when they arrive on Mars or other celestial bodies. That could undermine the validity of future scientific discoveries and complicate the search for genuine extraterrestrial life. All surfaces, tools, and spacecraft components are wiped down with alcohol and other cleaning agents. And additionally, all components are individually wrapped and thoroughly cleaned before being moved into the sterile environment. Both High Bay 1 and 2 is equipped with air filtration systems that cycle the air 70 times per hour to ensure that it remains free of contaminants. Number 6. The Oklo Natural Nuclear Reactor Study. The Oklo Natural Nuclear Reactor Study is a rare phenomenon that challenges our understanding of nuclear energy and the Earth's geological history. Situated in Gabon in West Africa, this naturally occurring nuclear fission reactor was active around 2 billion years ago, long before humans could harness the power of nuclear energy. This reactor is located in a series of uranium deposits in Gabon, which were discovered in 1972. The initial clue to its existence came when physicist Francis Perrin, while working at a nuclear fuel processing plant in France, noticed an anomaly in the uranium ore sample taken from the Oklo site. The sample displayed an unusual ratio of uranium-235, one of the isotopes necessary for nuclear fission. In essence, the conditions were right for the uranium to undergo fission naturally. This fission process in this context was maintained by water acting as a neutron moderator, allowing reaction to continue over thousands of years. The study of this reactor and the materials from the site is not without its risk. A significant challenge comes from the lingering radiation from the uranium and the fission byproducts that still exist at the site. While the reactor itself is no longer active, the materials left behind, such as uranium, plutonium, and other isotopes, remain radioactive, presenting potential hazards to scientists. This Oklo reactor provides a natural, rare analog for studying nuclear processes that have far-reaching implications in both environmental science and nuclear waste management. If a natural reactor can safely contain radioactive material for billions of years, the research from Oklo helps guide efforts to design human-made systems that can do similar things, and hopefully contain nuclear waste for extended periods, ensuring that these materials don't pose a risk to the environment. Number 5. Sandia National Laboratories. Sandia National Laboratories, established in 1949, is one of the United States' most high-risk research facilities, driven by the mission of ensuring national security through science and technology. Located in Albuquerque, New Mexico, Sandia is a key player in developing advanced technologies that support the nation's defense infrastructure. The origins here of it date back to World War II, when the U.S. Army established a facility known as the Z Division at Kirtland Air Force Base near Albuquerque. This division was responsible for non-nuclear aspects of weapons development for the Manhattan Project, which culminated in the creation of the first atomic bomb. In 1949, this facility was officially named Sandia National Laboratories, and its focus expanded from atomic weaponry to a broad array of defense and security-related technology. The laboratory is known for its work on nuclear weapons development, but it's also at the forefront of research in other areas such as energy, materials science, and autonomous systems. Among its many significant achievements, Sandia was home to some of the earliest and fastest supercomputers in the world, including the ASCII Red and ASCII Red Storm, which were used for advanced simulations relating to nuclear weapons. But in addition to the nuclear deterrent, Sandia is involved in other numerous high-risk projects. They delve into cognitive science, physics, and computational biology, as well as environmental concerns like hazardous waste disposal. The breadth of research at Sandia speaks to the immense responsibility and the risk the lab shoulders, making it a critical institution in the pursuit of national security. Sandia is also engaged in research involving energy weapons and autonomous systems. Now, these energy weapons, such as directed energy devices, can have devastating effects on targets, and developing these technologies involves understanding on how to control and harness enormous amounts of energy. Autonomous systems, meanwhile, pose a set of unique risks in terms of reliability, ethical concerns, and potential unintended consequences. Workers at Sandia must undergo thorough security clearances, and they're subject to constant monitoring while on premises. And in terms of physical safety, Sandia employs various safeguards, including fail-safe mechanisms in its experimental setups and safety measures that ensure the handling of radioactive materials is done properly. The Z machine, for instance, is designed with extreme caution to prevent any mishaps during its testing of materials at high temperatures and pressures. Number 4. The Tokamak Fusion Test Reactor. The Tokamak Fusion Test Reactor was one of the most ambitious experimental reactors built in the quest for controlled nuclear fusion. Located at the Princeton Plasma Physics Lab in New Jersey, this facility was designed to achieve the breakthrough of scientific break-even, a pivotal moment where the energy produced by fusion reactions equals or exceeds the energy input required to start them. Although the TFTR never achieved break-even, its work paved the way for numerous advances in fusion research. However, the nature of the experiments and the extreme conditions under which they were conducted meant that this lab operated one of the most high-risk environments for scientific research. Construction on the TFTR began in 1980, and the reactor became operational in 1982. TFTR's main objective was to reach scientific break-even by testing plasma with a deuterium-tritium fuel mixture, this combination most suitable for power generation. This was a significant leap from earlier experiments that used deuterium alone. This plasma, composed of deuterium and tritium, would be heated to temperatures exceeding 200 million degrees Fahrenheit, way hotter than the core of the Sun. The reactor aimed to demonstrate that these conditions could be maintained long enough for fusion reactions to take place at a scale sufficient for power generation. As the reactor advanced through its operational years, it achieved several notable milestones. For example, in 1994, it set a world record by producing 10.7 megawatts of fusion power, an impressive achievement, though still short of the break-even goal. Managing such high-energy reactions is no small feat. Any equipment failure, whether it's a malfunction in the magnetic coils, cooling systems, or plasma heating devices, can lead to disaster. For instance, if the magnetic fields fail or become unstable, the plasma could lose confinement and come into contact with the reactor walls. Even though fusion itself is much safer than nuclear fission in terms of waste and radiation, the sheer energy involved in maintaining these conditions is a risk factor. Moreover, the tritium used is radioactive, though it's handled in a carefully controlled manner. As such, the reactor's operations require careful planning and precision to prevent any unintended exposures. Number 3. Zoonosis Research Facility. The National Bio and Agro Defense Facility, located in Manhattan, Kansas, is one of the most advanced and high-security labs in the world. Officially operated since June 2023, it specializes in studying zoonotic diseases, those that can jump from animals to humans, as well as high-consequence foreign animal diseases. The NBAF was conceived as a replacement for the Plum Island Animal Disease Center, which had been in operation since 1954 on a secluded island off the coast of New York. While Plum Island made substantial contributions to safeguarding U.S. agriculture by studying diseases such as foot and mouth disease, its aging infrastructure and inability to handle biosafety level 4 pathogens highlighted the need for a more advanced facility. The 574,000 square foot NBAF is equipped with cutting-edge tech and infrastructure, including labs rated up to BSL-4. Approximately 10% of their research is conducted in those labs and focusing on diseases like the Nipah virus and the Hendra virus, which are known for their high fatality rates. All staff here are rigorously trained and emergency protocols are in place to respond to any potential breaches swiftly. Despite these precautions, though, the history of high-security labs demonstrates that accidents, though rare, do happen. Zoonotic diseases account for over 60% of infectious diseases in humans, with recent outbreaks such as COVID-19 highlighting the devastating potential of these pathogens. By studying them in a controlled environment, the NBAF provides critical insights that can help prevent and mitigate future pandemics. By combining cutting-edge research with state-of-the-art safety, the NBAF aims to address some of the most pressing challenges in public health and agriculture. However, its high-stakes work also shows the importance of vigilance and continuous improvement. As outbreaks become increasingly frequent in our interconnected world, facilities like the NBAF will play a central role in safeguarding human and animal health. Learning from past incidents and maintaining rigorous safety standards is going to be essential to ensure that this cutting-edge facility fulfills its mission without compromising public trust or safety. Number 2. CERN's Antimatter Factory in Switzerland. Hidden within the CERN research facility near Geneva, Switzerland, lies the Antimatter Factory, a site dedicated to some of the most groundbreaking and high-stakes research in modern science. While CERN is best known for the Large Hadron Collider, which investigates fundamental particles, the Antimatter Factory focuses on creating, studying, and containing one of the most mysterious and dangerous substances, antimatter. Now, antimatter can be thought of as the mirror opposite of regular matter. It's composed of particles that are identical in mass to their matter counterparts but carry an opposite electrical charge. For example, the antiparticle of a proton is the antiproton, which has a negative charge. When matter and antimatter meet, they annihilate each other, converting their mass entirely into energy. Now, this reaction releases energy on a scale far beyond that of any chemical or nuclear process. A single gram of antimatter, for instance, could unleash the equivalent to a nuclear bomb. Fortunately, though, such a quantity is almost impossibly difficult to produce. Since the antimatter factory began operations in '95, it's created fewer than 10 nanograms of antimatter, at an estimated cost of over $62 trillion per gram. Handling antimatter is inherently risky, of course, because it annihilates upon contact with other matter, releasing massive amounts of energy. Even a tiny amount, if not contained properly, could cause a highly destructive reaction. Now, antimatter is stored in devices called penning traps, which use powerful magnetic and electric fields to keep it suspended in a near-perfect vacuum. This prevents it from coming into contact with the walls of the trap, which are made of normal matter. Now, these traps are cooled to temperatures near absolute zero to stabilize particles even further and ensure they remain under control. Now, creating antimatter is also a highly inefficient process. When high-energy protons are smashed into a block of iridium, only a tiny fraction of the resulting collisions produce antiprotons. The installation of the extra-low-energy antiproton ring in 2018 dramatically improved CERN's ability to capture antiprotons, increasing efficiency from less than 1% to nearly 70%. Understanding antimatter could shed light on the asymmetry between matter and antimatter in the universe, help refine the standard model of particle physics, and possibly lead to new technologies. For instance, antimatter has the potential application in medical imaging, where positron emission tomography scans already use tiny amounts of antimatter to detect abnormalities in the body. Additionally, studying antimatter could have implications for future space travel. Theoretically, antimatter could be used as an incredibly efficient fuel source, as it releases far more energy per unit of mass than any chemical or nuclear reaction. Number 1. The Texas Biomedical Institute. The Texas Biomedical Research Institute, known as Texas Biomed, is a leading center for groundbreaking research in virology, immunology, and genetics. It's located on a 200-acre campus on the northwest side of San Antonio, Texas. This institute is one of the most unique in the world. Its combination of advanced study, a focus on infectious diseases, and the housing of high-containment pathogens puts Texas Biomed in a league of its own. Founded in 1941 by philanthropist Tom Slick as the foundation of applied research, Texas Biomed originally focused on agriculture, natural sciences, and medicine. In 2011, it adopted its current name, reflecting the emphasis on tackling some of the most pressing health challenges in the world. The campus houses over 60 doctoral-level scientists, along with more than 360 support staff, who focus on identifying treatment, vaccines, and diagnostics for diseases that affect millions globally. One of the Institute's standout features is the Southwest National Primate Research Center, which is home to approximately 2,500 non-human primates. These animals are essential for developing treatments and vaccines for diseases like Ebola, HIV, and tuberculosis. Additionally, they operate the only privately owned Biosafety Level 4 lab in the United States. However, working with such high-stake pathogens requires extraordinary precautions. The facility is equipped with airtight rooms, HEPA filtration systems, and decontamination chambers. Every movement within the lab is carefully monitored to prevent accidental exposure or contamination. The facilities here host some of the most dangerous pathogens on the planet, including those that cause diseases like Ebola and Lassa fever. A small lapse in any safety protocol could have significant consequences. Incidents at Texas Biomed have brought attention to the challenges of managing such a complex operation. In April 2018, 4 baboons escaped from the facility, raising questions about the containment protocols. While the animals were recaptured the same day and thankfully posed no threat to the public, the existence of facilities like this is not without controversy. The dangers posed by emerging infectious diseases and potential bioterrorism make high-containment labs like Texas Biomed essential, as well as a bit worrying. These facilities now allow scientists to study pathogens in a controlled environment, develop countermeasures, and respond to outbreaks. Without such research, humanity would be far less prepared to tackle another global health crisis. Thanks for watching, everybody. Stay healthy. I'll see you next time. Thank you to our channel members.